Hello and welcome to Chapter 11, Mathematics and the Arts. This is Unit 11A, Math and Music. So first of all, let's talk a little bit about sound, right? Like, what is this thing we call music? Any vibrating object produces sound. These vibrations produce a wave. Most musical sounds are made by vibrating strings, reeds, or columns of air. One basic quality of sound is pitch. The shorter the string, the higher the pitch. All right. Now, the frequency of a vibrating string is the rate at which it moves up and down. The higher the frequency, right, the higher the rate that it moves up and down, the higher the pitch. And these are measured in cycles per second. We're going to see CPS a lot. This is not Child Protective Services. This is cycles per second. The lowest possible frequency for a particular string, called its fundamental frequency, occurs when it vibrates up and down along its full length. Waves that have frequencies that are integer multiples of the fundamental frequency are called harmonics. All right, so if you have multiple waves and they all have integer multiples of the same frequency, they're in harmony. Now, what is this all about? So the fundamental frequency is what the string does along its full length, right? The string vibrating up and down at its fundamental frequency. Twice its fundamental frequency. Notice that twice the fundamental frequency. How many times does it happen in this? It happens twice. And they're half as long. And 4 times its fundamental frequency. The waves are 1/4 as long as those of the fundamental frequency. All right, so it's like you could put, if you have a string attached, right, and then cut it in half, use your fingers to pinch it down and pluck it, and you'll have the same, but twice as high. All right, so raising the pitch by an octave corresponds to a doubling of the frequency. Now that's weird. An octave, really screaming 8, right? Oct screams 8. But it corresponds to a doubling of the frequency. Pairs of notes sound particularly pleasing when one note is an octave higher than another note. An octave is the interval between, so you can start anywhere, but let's just start at middle C and the next higher C. For example, middle C has a frequency of 260 cycles per second, and the C above middle C is double that, which is 520 cycles per second. So the musical tones that span an octave comprise a scale. Excuse me. The musical tones that span an octave, right, comprise a scale. Most of us are familiar with the 7-note or diatonic scale that corresponds to the white keys on the piano. You may wonder why it's 7 notes. If we start at A, B, C, D, E, F, G. That's 1, 2, 3, 4, 5, 6, 7. And then we return to A. So the octave returns us to A, although there are only 7 notes in one scale. All right, so that's why it's 7 and not 8. It's kind of 8 because we return to A or C or wherever we started. While the Greeks had the diatonic scale, Johann Sebastian Bach adopted a 12-tone scale, which is called the chromatic scale, and it corresponds to both the white and black keys on a modern piano. Some of you may have learned this as a 13-tone scale. That includes all the sharps and the flats, and just like the octave, right, the diatonic, it starts where it ends, so that makes the 13th. On the 12-tone scale, 2 consecutive notes on the piano keyboard are separated by a half step. And the keys really tell you which tones have the half steps and which ones do not. For each half step, the frequency increases by some multiplicative factor. We're going to call it F factor. Okay, so middle C has a frequency of 260. Middle C is used frequently as a reference. I believe the A below middle C has a frequency of 220, and that is the one that they frequently use to tune. But I'd have to check to be sure, but I'm about 98 and 44, 100% sure. So let's look at the frequencies of the notes. This factor, the ratio of the frequency to the preceding note, the 12th root of 2, where does that come from? Well, Bach, right, has 12 different notes before we double, and that's all it is. 12 little steps to get to 2. So if I multiply 1.05946 by itself 12 times, I should get an answer of 2. All right. So 260 is the cycles per second is the frequency of middle C. If I multiply it by it's middle C. So multiply that by 12th root of 2. I'll get 275. Oh my goodness, I'm not even reading this table to you right. Really? Do you need me to read this table to you? So the different frequencies in cycles per second and the ratios, if we take it exactly at a step, notice that these values sometimes look very close to an actual good fractional value, but they're not precise. All right, keep going. We have sharps, we have flats. We didn't call any of them flat, we just called them sharp instead. We have a sixth, various ratios, and then we multiply it enough times, we get to 2. Wow. Because of the whole number ratios in the table are not exact, tuners and musical instruments have the problem of temperament, which can be demonstrated as follows. So we're going to start at middle C with a frequency of 260 cycles per second. We're going to use the whole number ratios, that 5/3, the 4/3, and so on. We're going to find the frequency if you raise C by a sixth to A, and then raise by a fourth to D, then lower D by a fifth to G, and lower G by a fifth to C. So I'm going to raise a sixth and a fourth, and I'm going to lower a fifth and a fifth. 6 and 4 makes 10, 5 and 5 makes 10. What goes up seems to have come down. Are we at the same frequency? Here we go. According to the table, raising a note by a sixth increases its frequency by a factor of 5/3, approximately. So the A above middle C is 5/3 times 260, which is 433 and a third cycles per second. If I raise this by a fourth, right, so 4/3, musical a fourth, mathematical 4/3, I'll take that 433.33, multiply by 4/3 to get up to D. I'm at 577.77 cycles per second. So I went up a sixth, then went up a fourth. Now I'm going to go back a fifth, which is a factor of 2/3. 2/3 times a 577.7. Why is... Yep, lowering by a fifth gives us 2/3. We saw that in the table. To G gives a frequency of 2/3 times 577.77, or 385.18 cycles per second. And if we lower by another fifth with another factor of 2/3, we get back to 256.79, which should be middle C, but we know that middle C started out exactly at 260 cycles per second. So if we use these whole number ratios, we don't get that same value again. Up a sixth, up a fourth, down a fifth, down a fifth. Turns out it's not exactly equal to 1. It's close, right? It's just a little bit short of that whole that we need as we move these. We could instead use an exponential function to find any frequency on the scale. Notice that Q, if Q sub 0 is the initial frequency, then the frequency of the note n half steps higher. Q is the frequency we're looking for, and that's going to be Q sub 0, our initial frequency, multiplied by our factor, our multiplication factor to the power of n. So we know that multiplication factor, that was 1.05946, the 12th root of 2. That's going to be multiplied to the power of n times our initial note. Let's look at an example. Use the exponential growth law to find the frequency of the note a fifth above middle C, the note 1 octave and a fifth above middle C, and the note 2 octaves and a fifth above middle C. So we let the frequency of middle C be the initial value and set Q sub 0 equal to 260 cycles per second. Table 11.1 shows that the note a fifth above middle C is G. See, this is where my music education as a drummer, and I didn't pay attention to my sharps and flats. Here we go. C, D, D sharp, E. Oh, that's not true. There is a C sharp, huh? C and C, C sharp, D, D sharp, E, F, F sharp, G, G sharp, A sharp, B. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Are you serious? Look at that. I think I pulled it off. So if we go a fifth above middle C, that's 1, 2, 3, 4, 5, 6, 7 steps to get to the G. So we let n equal 7, and that's how we get the value. We ask it to move a fifth, so we always reference the table for this section to make sure which one you're looking for. Wow. The note 1 octave and a fifth above middle C is that 7 steps that we just saw, plus the 12 of the scale. So we get 19. So we'll use 19 as our exponent. Multiply 260 times 1.05946 to the power of 19, and I'll get 779 cycles per second. And then I can go 2 octaves and a fifth above middle C, and we'll end up with 1,558 cycles per second. That's a lot of movement on that string. All right. But we live in the digital age, and until the early 1980s, almost all musical recordings were based on the analog picture of the music, and that's the LPs, right? The records, the vinyl. But today, most of us listen to digital recordings of music. When a recording is made, the music passes through an electronic device that converts sound waves into an analog electrical signal, which is then digitized by a computer, just using ones and zeros. It's really kind of crazy. That's it for music and mathematics. Thank you so much for listening.